Have you ever really thought about the world that exists right at the edge of your vision? I'm not talking about deep space. I'm talking about right here, on your own skin, in the air, in a single drop of water. Today, we're going to take a journey into that unseen world, using the one amazing tool that makes it all possible, the microscope. It's a wild thought, but our world is just absolutely packed with life that we can't see. There's this massive, bustling ecosystem of bacteria, fungi, and viruses all around us. Seriously, they're on every single surface, in every environment, and they're shaping our world in huge ways, all while being completely hidden from us.
Okay, so let's get real about this. We throw around words like microscopic and invisible all the time, but what does that actually mean? What's the actual limit of what our eyes can do?
So this is it. This is the line. The smallest dot the unaided human eye can possibly see clearly is about 0.2 millimeters. Just to give you an idea, that's about the width of two of your hairs sitting side by side. Anything smaller than that, boof, it's just gone.
Now look at this, because this is where the scale of the problem really hits you. A typical little bacterium is around 0.002 millimeters. That's 100 times smaller than the absolute smallest thing our eyes can even register. We're not just talking a little blurry here. We're talking about a completely different universe of size.
So how in the world do we bridge that massive gap? How do you build something that can actually peek into that hidden universe and bring it back for us to see?
Well, it turns out that to unlock that microscopic world, any microscope, from the one in your high school classroom to some crazy advanced research machine, has to master three basic things. You can think of them as the three essential keys to seeing the small.
First up, and you could argue it's the most important, is resolution. Now, this isn't about making things bigger, it's all about making them clearer. It's being able to see two tiny things right next to each other as two separate things, instead of just one big fuzzy blob. Without good resolution, all you get is a bigger blur.
Second, you've got to have contrast. Think about it. Most living cells are pretty much just tiny, see-through bags of water. If you shine a bright light right through them, they're going to be totally invisible against that bright background. Contrast is what makes that little object pop so you can actually see it.
And finally, we get to the one we all know and love, magnification. This is just making the object look bigger. But here's the catch. Magnification is totally useless on its own. If you don't have good resolution and contrast, all you're doing is making an invisible, blurry thing bigger. These three keys have to work together.
And here it is, the instrument that brings them all together, the classic bright field light microscope. Light shines up from the bottom, goes through the specimen. The objective lens, that's the one right over the slide, does the first big round of magnification. Then that image gets magnified again by the ocular lens in the eyepiece before it ever gets to your eye.
In the math to figure out the total magnification, it's super simple. You just multiply the power of the eyepiece lens by the power of the objective lens you're using. So a standard 10x eyepiece with a powerful 100x objective lens. Bam! You've got a total magnification of 1,000 times.
But, that basic bright field scope, it isn't the perfect tool for every single job. So over the years, scientists came up with a whole family of different light microscopes, and each one is a really clever solution to a very specific problem. Let's check them out.
So here's our first challenge. A lot of the time when you stain a cell to give it contrast so you can see it, you also kill it. So what do you do if you need to watch a living, moving thing, especially if it's really thin and hard to spot?
This is the brilliant idea behind the dark field microscope. Take a look at the light path on the right. There's a special little disc that blocks the direct light coming from underneath. So the only light that gets into the lens is the light that actually bounces off the edges of your specimen. And what you get is amazing, a brightly glowing object on a pitch black background.
And this is exactly what it's for. It's perfect for watching living, unstained cells, and especially for studying motility. Watching microbes actually swim around in real time. It's also super important for finding really thin bacteria, like spirochetes, which would be totally invisible under a normal microscope.
All right, next puzzle. How do you see the inside of a living cell? All those different parts, like the nucleus or the mitochondria, they're not just tiny, they're also almost completely transparent. They have pretty much the same density as the water around them.
Okay, this is where the physics gets really cool. The phase contrast microscope uses this elegant trick. See, as light passes through different parts of a cell, it actually changes speed just a tiny bit, kind of like a runner slowing down when they hit a patch of mud. You can't see that change with your eyes, but the microscope converts those invisible phase shifts into visible differences in brightness. And just like that, all those internal parts become clear as day.
But there's another way to do this, an even more targeted way. Instead of just messing with the light that passes through the specimen, what if you could make the exact part you want to see just light up on its own?
And that's precisely what a fluorescence microscope does. You use a special dye to tag a molecule or a part of the cell. Then you blast it with invisible high-energy UV light. That dye absorbs the energy and then shoots it back out as bright, visible light of a totally different color. It's basically like turning one tiny part of the cell into its own little light bulb.
But for all these clever ways of bending light, there is a hard physical limit to what light can actually see. To see something clearly, the wave you're using can't be bigger than the thing you're looking at. So to see something as ridiculously small as a virus, we have to ditch visible light completely and use something with a much, much smaller wavelength, a beam of electrons.
And the difference, it is just staggering. Just look at this comparison. The very best a light microscope can do is 0.2 micrometers of resolution. An electron microscope, 0.5 nanometers. That's 400 times better. And magnification? It jumps from maybe 1,500 times to over 100,000 times. We're talking about a whole new dimension of sight.
And this is the incredible machine that makes it possible, the Transmission Electron Microscope, or TEM. It's this massive piece of equipment that uses powerful electromagnets instead of glass lenses to focus a beam of electrons through an unbelievably thin slice of a specimen.
But seeing things at this crazy scale requires a really intense preparation process. The sample has to be stabilized with chemicals, completely dried out, embedded in a solid block of plastic, and then sliced with a diamond knife into sections that are 1,000 times thinner than a single human hair. It's incredible.
So, we've gone on this whole journey, right? From the absolute limits of our own eyes, through all these clever ways of bending light, all the way to using electrons to see the tiny machinery of a virus. Every step was a huge leap into a world that was invisible just moments before. And it really makes you wonder, what other unseen worlds are still out there just waiting for the next big leap in how we see?